the first two talks this morning, we heard a lot of interesting things, a lot of theory, a lot of uncertainty, a lot of the challenges we face in understanding Uranus. Our next two talks, we're going to now get into more of the practical realities of how we measure the things we might want to measure, and then it'll be how we actually design and what compromises you have to make when you're flying a space mission to collect some of those measurements. But starting out, we have Krista Soderlund, checking my notes. You are a professor at the University of Texas at Austin Institute for Geophysics. She is broadly interested in fluid dynamics, and a lot of her current work is on icy satellites, but particularly relevant to our study. She's also interested in how these convective motions generate magnetic fields, particularly on giant planets. She's a member of the Europa Clipper science team and has been involved in several mission studies looking at Uranus missions. So as I say, I think all of our speakers, maybe most of us in this room, have a mix of theory and ties to space missions. And then it was as I was preparing these notes, I realized every one of our speakers has a connection to Southern California because Krista got her PhD from UCLA. So Krista will tell us about the measurements that we hope to make to better understand Uranus's interior. So thank you, Krista.
Okay, thanks very much. So I'm really delighted to be here to be able to tell you about some of these measurements to try to understand Uranus's interior better. So I'm going to break the talk into three main parts. The first one is really going to focus on the traditional approaches to understand the giant planets, thinking specifically about Uranus using Voyager 2 observations. And then we'll look a little bit at how we have this old data, quote unquote, from Voyager 2, and there's all of these new advances in analysis techniques, so we can kind of leverage what we've learned from this mission long ago and reinvigorating those studies. And then we'll look towards lessons from our counterparts in the outer solar system, including Jupiter and Saturn and exoplanets. So that's going to think about things like the Galileo probe, the Juno spacecraft, and the Cassini mission. And then also some exoplanet observations. And then we'll just briefly wrap up with knowledge gaps that we can use to try to build upon some of these observations. All right, so jumping into the Voyager 2 observations. So Voyager 2 flew by Uranus in 1986 at, I think, an altitude of about 82,000 kilometers at its closest approach. And it had an investigation suite composed of 11 different instruments. So I'm going to highlight a few of these as examples of how they are relevant to the interior of Uranus. So that's going to include the ultraviolet spectrometer, UVS. It'll include the infrared interferometer spectrometer, IRIS. It'll include the planetary radio astronomy experiment, PRA, the triaxial fluxgate magnetometer, the MEG, and the radio science system, RSS. So just to kind of start at the highest level of what do we kind of know from some of these observations. And the first one we'll think about is the physical shape, and you heard about this from Ravid. So one of the ways that they're able to get these shape measurements is looking at radio occultations. So when the spacecraft flew by, it was able to do an occultation, so it was able to look through the atmosphere, and that gave you these two constraints up here, these little dots, in terms of the radius at the 1 bar level as a function of latitude. So you have these two constraints up here, but then you can also take the gravity measurements and also measurements of the zonal winds to infer this profile from the equator all the way to the poles. So that gives you a measure of the equatorial shape pretty well, and then you have inferences for the polar latitudes as well. And then moving on to the rotation period, this is another thing that you heard a little bit about from Ravid, and there are two ways that the Voyager 2 mission started looking at how to estimate the rotation rate. The first was using this radio astronomy technique, so it's basically going to find these periodic variations, and then they do a Fourier analysis. They're able to find this peak in terms of how frequently they find these peaks in the PRA experiments. And that gives you an estimate of about 17.24 hours. Then you can also complement that with measurements from the magnetometer. So you're going to take a magnetic field model and you're going to try to fit that with the observations. And then where they have a minimum in the misfit is the estimate for the magnetic rotation rate. And that gives you an estimate of 17.29 hours. So they're roughly consistent. So as I mentioned, we had these measurements of the magnetic field. And when you look at the magnetic field of Uranus far away, it looks like an offset axial dipole. So that basically just means you have, say, like a bar magnet in the center. It's not going to be aligned with the center of the planet. It's going to be closer to one side, and it's also going to be tilted away from the rotation rate, the rotation axis. So that's why it's called this offset tilted dipole. But you can look at this a little bit from a different perspective if you consider what the field likes at the planet's surface. So then you're going to have a lot more of the smaller scale features that then you are not taking into account in this type of kind of big picture view. And what I'm showing here is the surface magnetic field, radiomagnetic field is a function of latitude and longitude. The positive contours are going to be where the magnetic field comes out of the planet, and the negative contours are where the magnetic field lines go into the planet. And then I have a very poorly drawn marker of the magnetic equator, and you'll notice that there's not only one, but there's two of them, which is different from what we have on the Earth, which is a dipole. So you have a much different, more complex magnetic field structure. And you can decompose this into a spherical harmonic degree analysis, and that will show you that the dipole and the quadrupole components are comparable to or even greater than the dipole components. So it's a much more complex field than we had seen before. So then we can look to the internal structure, and this again relates to the magnetic field just in terms of the magnetic field is generated deep in the interior. So you're going to need to know like what the interior is made out of and how that dynamically operates, and we'll get into that a little bit more. So when you're flying by the planet, you're going to experience these perturbations due to the distribution of density within the planet. So those spacecraft measurements are going to be reflected in these density profiles as you take these gravitational moments and you input them into the internal structure model that Ravi talked about. And then this plot right here showing density as a function of normalized radius is just some of the very first internal structure models. And again, you can see that there's kind of a possibility of a somewhat continuous profile, or you could have a more distinct three-layer structure. So you're able to have you are left with a lot of uncertainty near the center of the planet because, as you heard, there's a lot more sensitivity through the gravitational moments the further out towards the radius as you go. And one of the other things to really take to heart here is that these are really non-unique, especially when it comes into terms of relating this density profile to the composition and the temperature. So just an example of that is here's just different densities for, say, pure ice, if you have a combination of 80% rock and 20% gas, and then so on. In terms of 75 rock, 25% gas. And you can get really, really similar densities depending on these different compositional mixtures. So that's one of the examples of why you can't just say, I got a density here, this is what it's going to be. And then if you can take that and then you compound it of like how hot those materials are, that temperature is also going to influence the density of that material. Okay, so one of the other aspects that is really significant for Uranus is that when we did this flyby, we're able to do these infrared measurements. And from that, you're able to get things like how the temperature of the 1 bar pressure level varies as a function of latitude. And you'll see that it is relatively smooth, but it does have a couple dips apparently at mid-latitudes. You're also able to see how the brightness of the body varies with phase angles. So that's basically just how much of the disk is lit up versus dark. And you're also able to measure the emitted flux across a range of wavelengths. So if you're able to kind of take all of those ingredients together, you can come up with something called the energy balance. And that's going to be the ratio of the emitted thermal flux to the amount of heat that is absorbed from solar radiation. And this is just a table summarizing some of the very early studies, and it gives an upper bound of the energy balance. And this most recent investigation gave an upper bound of 1.14, but it can be as low as like 1.01. So there could be very, very little heat coming out of the internal heat coming out of Uranus. So that's one of the big conundrums in terms of the internal structure, as we heard a little bit about before. Okay, and we've heard a little bit about composition, and I won't go too much into detail here, besides to say that there was, I mentioned this infrared spectrometer, but there was also the ultraviolet spectrometer. So you're able to take these spectra data and make estimates of what like the columnar abundance and the mixing ratio is for a bunch of different molecules in the atmosphere. So you're able to measure like ammonia, and carbon monoxide, and all of these other different things in the atmosphere. So that gives you some constraints on what the at least observable atmosphere is going to tell you. So then you can relate that to kind of the solar estimates in terms of like the CH4H2 mixing ratio is about 25 times solar. The ammonia to hydrogen volume ratio is depleted, and that could potentially be due to maybe some dissolution in the ocean. There are some very rough estimates of this helium mass fraction, and it looks like it's roughly similar to the solar value. So that kind of implies that you haven't had this like helium rain process happening in Uranus. And the preliminary, like the first estimates in terms of the water to hydrogen mixing ratio is estimated to be about 9%. Okay, so that's just some of the very first analyses using some of these Voyager 2 observations. So next we can go into how can these measurements be reanalyzed using more modern techniques, and we'll kind of go through some of the same things that we did before to give you an update on how things have changed and stayed the same compared to the previous work. So first, thinking about the shape and rotation period. So Ravik talked about this earlier, but you can take some of these shape measurements and you can have these measurements of the zonal winds, and you can try to minimize the dynamical shape. By doing that, you're able to get a different rotation rate estimate. So that turns out to be about 16.58 hours as opposed to the Voyager data of about 17.2. So there's a substantial difference in terms of the rotation rate. So that's one of the reasons why it's so important to figure out which is the real rotation rate. Does it vary in time like it does on Saturn? And so on and so forth. And we also heard about how the rotation rate has an influence on the shape of the body, because that will, for example, affect the oblateness. And then I also wanted to point out that there was a more recent analysis of the UV spectrometer data, also looking at estimates of the rotation rate, and that's by looking at what's shown up here. So they do another one of those minimization fits, and they find a rotation rate that's similar to the magnetic field data. So there's something going on in terms of why these mechanisms approaches yield different results. Okay, so we've also kind of heard about how we are able to use these gravity moments and a few of the other ingredients to get estimates for how density is distributed throughout the planetary interior. And one of the directions that I think a lot of the field has been going towards is composition agnostic models. So these are more of the empirical approach to see what different density profiles could fit the gravity data. So then you're able to still see that really strong variation, a large amount of uncertainty at near the center of the planet, but you have a relatively good refinement of that at higher latitudes or higher altitudes. And then we're also kind of moving with advances in the field in terms of we know more about the equations of state. So we've been able to take advantage of a lot of these new data from like the high pressure, high temperature mineral physics communities and take those results and incorporate into the models. And that's another way that all of these models have been improving over time compared to the early studies. And one of the other aspects is that we're also moving towards non-adiabatic regions. So the earlier models often assumed this 3-layer structure, but they also assumed the bodies to be fully adiabatic. But then we've heard that can be problematic. So there's been ideas that you could have non-adiabatic regions, for example, a thermal boundary layer that could, say, develop between the kind of the gas-rich region and more of like, say, an ionic ocean. So in that case, you could have a very, very hot interior, and that's going to be this like hot Uranus model. On the other hand, if you have something that is fully convective, you're going to have a much colder central temperature. And then you'll have different amounts of these different materials within the bodies, and that's more of like an icy Uranus scenario. So in addition to thinking about how the temperature structure could have these potential discontinuities, you can also think about how this relates to the composition changing with depth. And this really comes into play in terms of thinking about mixtures of water and rock, as we've been hearing that seems to potentially have a big role in the internal structures of Uranus and potentially Neptune as well. So this has been some work from Vazan and Haled in 2020 that basically just looks at the metallicity as a function of time for a bunch of models that fit their gravitational and other constraints. And then the bottom plots are going to show you temperature for all of these different models. So the thing to kind of note here is that you have different degrees of mixing across all of these different models. So then there's scenarios where you could have potentially an unstable temperature gradient, but a stable compositional gradient. So then in that case, you would have a less efficient mixing and dynamical interior. And this is just another way that I wanted to highlight how improvements in the equation of state and then general understanding of properties of these different materials comes into play in terms of these interior models and how they evolve over time. Okay, so there's also been work done at thinking about superionic ices. So I haven't heard too much talk about superionic ices yet, but they are, I think, really fascinating because they are what water turns into once you get into like really high pressures. So it's thought that you could have, if there's a lot of water in the core, you could have a solidifying superionic frozen core in Uranus. So that's kind of demonstrated schematically where you could have this rock layer and then you're going to slowly solidify in time this superionic ice layer, and then you're going to still have this fluid ice and then your outermost envelope. And one of the really interesting things in terms of working with the mineral physics community is that they're able to do things like measure the shear stress, and this is going to be of a superionic ice, and this is going to be that of liquid. So they're able to suggest that the viscosity of this superionic ice is going to be more like a solid than it is of a liquid. So that will have big consequences on the dynamical and orbital evolution and also the cooling time of the body. So one of the ways that you can look at that is if you incorporate this into a thermal evolution model, which is shown here, which just shows the effective temperature as a function of time. If you don't have this freezing core, you're going to have this red curve. But if you incorporate this freezing high pressure ice layer, you get a frozen core that's much more consistent with the temperature that we observe at the day that's still within the formation of the solar system. So it seems to be pretty consistent on that front. And one of the other things that is really, I think, quite fascinating about this model is that it also links to the satellite orbits. So this is really where taking a systematic view of the entire Uranian system comes into play, where you can think about how the orbits of some of the innermost moons, say Miranda, Ariel, and Umbriel, and how they evolve in time, will then feed back into the structure of the planet's interior. And part of the thing that allows that to happen is if you have this relatively high viscosity region that's changing over time, then you're going to have like a tidal Q factor that changes in time as well. So then that change in dissipation within the planet is going to lead to changes in the satellite orbits. And this will give some testable predictions, for example, the tidal love number, and also how the satellites are going to recess, which we could maybe measure with a future mission. So we've heard from Jonathan this morning about how we can use these different observations of the elements, like the Schnapps elements and also the noble gases, and use that to test these different formation and evolution scenarios kind of through this planetary abundance ratio compared to solar elements. So we're able to get these Uranus values largely from spectroscopic observations, and that's going to be shown by these kind of purplish colors here. So I just want to show that it's important to be able to think about how we can get additional measurements for these elements. We can match what we know about, say, Jupiter and Saturn and these comets, so we can have a holistic view of the evolution of these bodies. Okay, One of the other aspects to think about in terms of the interiors is we've heard about the discussion of a rock giant versus an ice giant. So there's this really nice diagram in Teenby et al. That kind of puts a path forward in terms of assessing whether you have a rock giant or an ice giant. And the things that they note are especially important are, in addition to observations, knowing things about the degree of mixing in the interior and the distribution of CO in the atmosphere versus the deep interior, and like eddy mixing ratios in the upper atmosphere. So there's a complicated picture to disentangle the rock giant versus an ice giant using atmospheric composition measurements as well. And then finally, we can think about the zonal wind depth. So we are able to do this a number of ways. So in 2013, Yochai Caspi did a nice analysis of the gravity data from Voyager 2, and they make an estimate that the zonal depth, so that's going to be this H factor, is going to have to be within these red bounds in order to match the gravitational estimates. So that basically puts an upper bound on how deep those winds could have gone into the interior. And more recently, there's been work that have been trying to couple these gravity measurements with measurements of the shape and the rotation rate and all of those uncertainties. So one of the ways that they do that is through like Monte Carlo simulations. So all of these dots are different models, and for Uranus and then for Neptune. And you notice that there is a large box of where the gravitational signals for the models are compared to the actual observed value. It is argued that this jump is due to the zonal winds. So then they're able to take that difference and apply that to things like the shape data in terms of making estimatable predictions. So that's what's shown here in terms of the radius of the planet as a function of latitude. So the initial fit is kind of this gray line, and then you could have kind of modified gravitational coefficients. But if you incorporate this differential rotation axis in terms of the zonal winds, you get these dashed lines. And you can see that there's quite a bit of spread, so you might be able to make some inferences about the zonal wind depth by measuring the shape at the poles as well. So there's another way that you can do this, and that's to look at ohmic dissipation. So ohmic dissipation is basically just how much heat is being generated magnetically in the system. So one of the things that you need to know for that is how the electrical conductivity of the interior into the atmosphere behaves. So they have some nice diagrams where they have a large number of interior models where they're able to get these different temperature profiles, and they have different compositions as well, and they're able to relate that into electrical conductivity profiles as a function of radius. I'll note that this plot is going across the whole planet, but this one is only in the outermost part of the planet. So they have a pretty wide range of what the possible electrical conductivities are going to be. And then they're able to take that and then combine it with the estimates of ohmic dissipation in terms of the magnetic field strength. And they're going to have two bounds in terms of these possible black lines, and then these colored lines are the models. So you basically want to make sure that you don't have more energy in terms of ohmic dissipation that is allowed by the planet. So that kind of limits the zonal flows to be within like the outer like 2 or 3% of the planet. And one of the other interesting thing here is that if you have these electrical conductivity variations and you also have a depth of the zonal wind, you could potentially make some predictions about how the interaction of these zonal flows of that electrically conducting fluid can lead to perturbations in the magnetic field signature. So there might be ways that you can search for these perturbations in the intrinsic magnetic field measurements to kind of test out some of these ideas. Okay, so then we can go back to the magnetic field. And one of the things that was done in 2009 by Herbert is they were able to add additional constraints to the intrinsic magnetic field using the footprints of the satellites in terms of the auroral ovals. So by doing that, they were able to go from a model resolved well to spherical harmonic degree 3 to spherical harmonic degree 4, which maybe doesn't sound like that big of a deal, but it's actually pretty awesome when you only have 3. And then when you do that, just to kind of show how that is significant, on this figure here, this is just showing the spherical harmonic degree 3 component, and you can kind of see how different that is compared to when you get one additional spherical harmonic degree. You get, the same structure, overarching structure is there, but you have a lot more detail. And you also have a stronger magnetic field in the peak spots than you did before. So as you learn more and more about the smaller scale structures of the field, it's not only going to look different, but you also potentially could have a different magnetic field amplitude, which then feeds into a lot of the other estimates of what the interior is doing dynamically, thermodynamically, and that feeds into the composition as well. So one of the other things that you can do is thinking about how the magnetic field is generated. So in order to have a magnetic field, you need to have an electrically conducted fluid that is moving around so that you're going to be able to convert that kinetic energy into magnetic energy. So the ingredients are going to be convection of some sort and make sure that it's electrically conductive enough. And there's been a number of hypotheses put forward to explain why the Uranus and Neptune have really different magnetic fields. One is that you have the convection in a relatively thin region outside of a stably stratified deeper fluid layer. And then you can also have a thin convecting region overlying a solid region, but that solid region needs to be more electrically conductive than the fluid layer. So those are kind of two ideas put forward by Stanley and Bloxham. And you could also say, does it really matter how thick or thin your dynamo region is? If it is convecting in an unorganized way, you could have an unorganized magnetic field. So those are just three of the hypotheses out there in the literature, and I'll just show you some results from one of the dynamo models that I ran. So this is the radiomagnetic field at full resolution in the models, and when I kind of filter out to only the spherical harmonic degree field, that is what this looks like. So you can kind of see like this is quite different from that. So that's one of the reasons why you really want to know the smaller scale structures. In all of these models, you get some type of differential rotation. So here, the blue is retrograde, the red is prograde. That leads to an overturning set of cells within the deep interior, so which that could relate to the transport of materials and mixing. And then just the bottom ones to show that we do this calculation in a full 3D rotating spherical shell, so they're pretty intensive. Then I want to move to lessons learned from Jupiter, Saturn, and exoplanets. So the first one is just the Galileo probe. So this had 9 experiments as part of it. And I'm just going to focus on 3, the helium abundance detector, the neutral mass spectrometer, and the Doppler wind experiment.
10 minutes.
Okay, thank you. So we talked a little bit about the importance of actually measuring the in situ composition of the body. So that's what the Galileo probe was designed to do. So they was able to get all of these different species and their abundances relative to the solar value. So ideally, we'd have something like this to plug into this diagram for Uranus and Neptune, ideally. And then it also had a helium abundance, so it was able to measure the helium mole fraction as a function of depth. So that would also be, I think, something very good to have based on some of the discussions after the last talk. And one of the other experiments that the probe had was the Doppler wind experiment. So this was where there was a probe and it was able to measure the zonal winds as it descended into the planet's atmosphere. And what this showed is that the winds actually reach even faster speeds and are sustained at those speeds until the probe was crushed at like 24 bars. So that was one of the first indicators that you could have these deep winds in the satellites. And this was supported by ground-based observations by the Very Large Array, where they found a really similar pattern in terms of the extended zonal winds. All right, finally, we'll go towards Juno's not finally. We're going to move to Juno. So here we had the gravity science, the microwave radiometer, and the magnetometer that I'm going to focus on. So one of the, I think, really big ideas that came out of Juno, at least from my perspective, is this idea of a dilute core. So I think that's given a lot of support to this idea that you could have some of that income, like not a discontinuous boundary between, like, say, ices and rocks. So that was been one of the, I think, the scientific aspects that really changed with Juno's. That got a lot more support. But I also wanted to relate this back to the equations of state. So the diagram that's shown here is just the extent of the dilute core and how much mass it contains. And all of these different colors are different equations of state. So you can see that it's quite sensitive to knowing how the materials at those pressures and temperatures behave, and that feeds into how large that dilute core is. One of the other things you can do with radioscience is that when you, say, do a flyby over a large vortice like the Great Red Spot, you're able to watch how that affects the traveling of the spacecraft. You're able to measure those perturbations. And by doing that, you're able to make estimates on how deep that vortex extends into the interior. So that was some nice work done, that the Great Red Spot would extend to, say, no more than 300 kilometers below the surface. So it's a pretty deep vortice, and you're able to do similar analyses with the zonal flows like we talked about before. We're also able to get really great magnetic field measurements with Juno. They're able to get to spherical harmonic degree 18, which is like awesome. And I'll also point out that that means we know Jupiter's magnetic field better than we know our Earth's geodynamo field, because the smaller scale features are masked by the crustal field. So it's pretty amazing that we know Jupiter's magnetic field better than the Earth. And then one of the things you can do is, this is the radiomagnetic field, say at the 1 bar pressure level, but you're also able to downward continue those fields to where you think the field is being generated. You can see you have a much more complex structure, which then also feeds into the dynamo modeling that I talked about before. So one of the other things that you can do if you have measurements that extend over time is you can look at secular variation, or how that field evolves over time. So this is some work looking at how the dipole moment changed over time from the 1970s all the way up to the mid-2000s. That's same for the dipole colatitude, and then also the dipole longitude. And by taking these evolutions over time and coupling them to like a geostrophic flow model, which I think probably is pretty reasonable, you can make estimates of what the geostrophic flow of that core is. So that's just some 2 maps looking at the flow in this geostrophic region, and then also the toroidal flow. So that's kind of the east-west ones. And you're able to get these kind of maps and flow speeds just using the evolution of the magnetic field over time. One of the other things that you can do, and this was a new paper by Kamiko Hori, is that if you have these really good measurements of the magnetic field, one of the things that you can look at is how this could lead to torsional oscillations. So that's basically going to be a wave motion in the interior that's generated by magnetic fields as a restoring force. And when you look at this, you're able to see that there is a correlation in the frequency of these restoring forces due to these torsional oscillations with frequencies of tropospheric weather anomalies of, I think, 4 to 6 years. So this suggests that the magnetic field in the deep interior is reflected in the evolution of the troposphere and how that evolves over time. And that's done through having these kind of torsional oscillations affect the heat flow, which then affects the zonal winds. So I thought that was a pretty cool coupling of the interior dynamics with the atmospheric dynamics. And then one of the other instruments that was new to the outer solar system that flew on Juno was a microwave radiometer. So this is going to measure the thermal emission down to about 100 bars. And one of the big things that it was able to determine was these maps of ammonia abundance, and also some estimates on the amount of water in the interior. So that's kind of just shown in terms of like the ammonia and also the water in terms of how enhanced that is relative to solar. And then next we'll move on to Cassini and lessons from Saturn. And here we'll look at the composite infrared spectrometer, the visible and infrared mapping spectrometer, the magnetometer, and then the radio science subsystem. So one of the things about Uranus that was so unique is it had this really low internal heat flux, like energy balance number. And I'm bringing this up for Cassini, and actually we're looking here at Jupiter from the Jupiter flyby, is that when this data was analyzed, it found that the emitted flux changed by a pretty substantial amount. So it is now at an internal heat value of like 7.5 watts per meter square, when before it was only 5.4 watts per meter square. So there's a significant deviation from what we measured from, I think, the Galileo time compared to what was measured by Cassini. So that suggests that either there was some uncertainties in those measurements, or it's potentially varying in time. And that seems to be the case
2 minutes.
for Saturn as well.
I have a question. Is that 7.485, is that accepted broadly, or is still 5.4 for the energy, like the heat flux of Jupiter still accepted?
It's a good question. I think it's accepted, but
Okay.
maybe we can talk later. One of the other things is that we're able to use the VIMS instrument and also the gravity system to look at perturbations in the rings. And then by doing that, you're able to look for these normal mode oscillations. And then from there, you're able to make some estimates about there being a dilute core in Saturn just by watching how the rings evolve in time. And that's what's shown in this diagram here. And then we can go to potential new directions that are moving forward, and that's Doppler imaging of the interior. So there's a relatively new paper looking at a Doppler spectroimager using the Jovial Jive system. And in this case, they're able to watch how the Doppler shifts in terms of things moving away or towards the observer. And then from there, you're able to make estimates of what the zonal flows of Jupiter is. So this is just kind of a proof of concept to say that you can, from the ground, measure the zonal winds. And if you're able to maybe get there, you could potentially look for like global oscillations that could tell you more about the interior. So that's basically just shown in terms of the observations that they're able to obtain, and then a degraded resolution of the winds that are observed. And then we heard a little bit about how looking at exoplanets also provides a more holistic perspective in terms of where Uranus and Neptune fit between rocky planets and the gas giants. And there's been some spectral detections that give some clues about the composition. And then the last one I want to bring up in terms of exoplanets is that there was recently observations of a Neptune-sized exoplanet that it had really strong magnetization and also a metal poor atmosphere. So we're able to get estimates of an exoplanet magnetic field through Hubble Space Telescope ultraviolet observations, which I think is really a promising technique that I'd like to learn more about. And then finally, just in terms of knowledge gaps, I just want to briefly mention the Uranus Orbiter and Probe, especially since it hasn't really been talked about in detail too much. So this was put forward as an option recommended by the Decadal Survey, and it considered an orbiter that had the following instrument suite, noting that there's room for that to evolve, but they needed to kind of size the instrument. Spacecraft, and that includes a magnetometer, a narrow-angle camera, a wide-angle camera, a thermal infrared camera, visible to near-infrared imaging spectrometer, a fields and particles suite, and radio science. And then the probe had atmospheric structure, mass spectrometer, a USO, and an orthoparahydrogen sensor. So this is just the science traceability matrix, and I just wanted to highlight a few different aspects in terms of determining the depth of the atmospheric winds through gravity and radio science, figuring out where the planet formed, looking at noble gases with the mass spec on the probe, these elemental and isotopic bounds also through the probe, global composition, and this energy balance by looking at the thermal infrared and visible near-infrared spectra. You want to understand the gravity field to understand how the bulk composition will change with depth. And also, does it have a fuzzy core? Does it have discrete layers? And you can do that through looking at the gravity field and also potentially ring oscillations. You want to know about the rotation rate, looking at the magnetic field, the shape, and the gravity. And then in order to understand the dynamo, you also really want to have a detailed structure of the magnetic field and its evolution over time. And then the last slide that I wanted to share is just some strategic supporting activities that were identified and slightly added onto by me to think about what processes influence the structure, evolution, and dynamics of giant planet interiors, thinking about Uranus as a whole. And I think has been mentioned in every talk so far, it's critically important that we get lab and numerical estimates of the high pressure, high temperature equations of state, the chemical reactions that occur there, and the transport properties. Like, I'd really love to know how viscosity, the thermal conductivity, the electrical conductivity, all vary as a function of radius for all of these different internal structure models. That's like my personal dream. It would be awesome. I think it's also really important that we keep developing these numerical and theoretical tools to analyze the existing data we have and try to leverage, incorporate any ground-based observations that we're able to do. And that includes the atmosphere, the interior, and the magnetosphere, because they're all really coupled. It's one body. So I think we have to think of this as a system and take advantage of that. And that kind of links into these continued data analysis and also the development of these new observational techniques. For example, this ring seismology and the Doppler imaging, I think, has a lot of promise, but also need a lot more work in order to assess their feasibility and size instruments and all that type of thing. I think it's also helpful to do this long-term monitoring of all of these different atmospheric phenomena, look for aurora, and see if there's anything from impacts that we can learn. And then finally, taking some lessons from the exoplanet community in terms of the distribution of exoplanets that are out there that relate to Uranus-sized bodies, and also trying to see if we can find out more about the magnetic fields of these bodies, because I think that would be another unique window that hasn't been really tapped yet in terms of the ice giants. So with that, I will end.